Tonight's presentation is what Astronomy for Changes is a not-for-profit organization. We're trying to support the proposition that astronomy, specifically and science generally, can be a positive for the world. Okay, and this is the first public presentation, hopefully of many. This is we have a website, we have a Twitter account, all that. You can go online and check it out. In the meantime, while we're waiting for folks to show up, you can get on a pad if you feel so inclined, if you want updates, emails. Okay. This is a fascinating topic, and it's one that my entire life I've often wrestled with this idea, some of which we'll discuss tonight. Are we forever going to be bound to our little corner of the universe? Or is there something more exciting and more and possible waiting for us as we progress further technically? Whether or not we can muster the social and other impediments to overcome our obstacles to get to the point where we can establish outposts on the moon, outposts on Mars. Will it be in my lifetime? I don't know. The younger people here tonight will be in your lifetime. So those are some of the things, some of the possibilities we're going to talk about tonight. Okay. This is just a brief overview of what we do, some of the affiliations that we have. As a scientist at Brookhaven, I teach at Suffolk. I'm a NASA Solar System Ambassador. Basically, I represent the space agency to the general public. Okay, advocate for the space agency's objectives, goals, and programs and missions. So, Einstein, in 1905, he worked in the Swiss patent. He moved to Switzerland. He was basically a scientist without a job. So he emigrated to Switzerland. He was applying for jobs. He had no job. He had his degree, but no work. So he applied to the Swiss government. And they gave him a job working in the patent office. And every day, he would look out the window, watch the train goes by, and across the street there was this big clock tower. And he often thought to himself, I'm putting myself in his shoes, they don't mind. He would think to himself, looking at the time, what would happen if we could actually sit on a beam of light? What would the universe look like? What would happen? 1905, during his Annus Mirabilis, or Latin, or miracle year, he publishes, along with three other very important works, the special theory of relativity. He did not get the Nobel Prize for this, by the way. He earned his Nobel Prize for his work on what they call the photoelectric effect, the basic premise that allows us to have solar panels. Basically, that light has a certain quantum of energy. When it interacts with a certain material, it generates an electric current. Okay, so that's what he earned his Nobel Prize for. Interestingly enough, out of his special and general theories, comes a whole, for the last 100 years, since the public law was, November 25th is actually the anniversary of his publication of special relativity, which we'll talk about. Okay, and so this thought experiment would come to play a key role in the development of the special theory. Now, there's two theories. The first one, special, was developed in 1905. It took him 10 years to work out the kinks and the mathematics to publish his general theory. The special theory is very specific. For those regions that are not undergoing any kind of acceleration or new changes, that's what the special theory relates to. The general theory of relativity applies these principles to the broader universe, where you have all kinds of dynamics in play. This is his famous, that first equation basically describes the universe. Everything in the universe can be described with this equation. This is the curvature of space. This is some constants. Now, going back to almost 300 years, Isaac Newton published his Principia Mathematica in 1687, wherein he describes the universe in all its grandeur. And he was quite content to explain it, the machinations of it, how it worked. But it took Einstein to describe the why. Yes, we have the sun, the earth orbiting the sun, the moon orbiting the earth. Everything can be described almost perfectly, with very few exceptions, using Newtonian's principles, Newton's principles. There's a few really kind of quirky little things like Mercury's orbit isn't precisely defined, or cannot be precisely described using Newton's ideas. Einstein to do that. So Newton describes the how. The why of it all is that space is really warped. How can space be warped? How can you even imagine that? Clearly, it's an abstraction. So if you consider a large sheet of rubber stretching across this room, you put, let's say you put a bowling ball, or maybe a grapefruit in the middle, it's going to make a little bump in it, right? The bigger that object is, the more massive it is, the deeper that bulge will be, to the point where if you put something so big, it'll just basically tear it. That's what we have as a black hole. Okay, and in the last few frames of that video we just played, that was a black hole. This here, this first term here in the equation describes the nature of the black hole itself. How much stuff is in it, how much mass it has, its size, its dimensions. Over here, we have a series of things like energy and momentum, things like that. So this is equal to this. Basically, you can describe every object in the universe using Einstein's equations. And it explains the why, not just the how, of why the universe works the way it does. Okay. The special theory of relativity has some very important ramifications. One thing is that nothing in the universe that has any mass to it can travel at the speed of light. travel and observe while riding on a hypothetical beam? Well, first of all, nothing that has any mass can travel at the speed of light. Okay, it's the universal speed. Light itself is the only thing that can travel at the speed of light, simply because light has no mass to it. Okay. Time would slow down as you approach light speed. Length would shorten in the direction of motion, and your mass would increase. And I will give you a flavor to the magnitude of those changes in the next few slides. But just to give you a little background into this idea of time, let's use time as a way to describe this. Some famous experiments were conducted in the 19th century. Michelson-Morley experiment one, where the proposition was that, well, the universe is pervased with this invisible substance called ether. You can't measure it, you can't interact with it, it's just there. Because the classic idea of a wave is that you need a medium for the wave to travel through. So the thinking was that space is a vacuum. What's the medium? So they invented this idea of an ether. And that idea persisted for a long time. There was two people. James Clerk Maxwell actually gave us a famous set of equations that says, well, light is a wave. And then there was, after Maxwell came Michelson-Morley. The idea was if the Earth is moving around the sun, moving through the ether, if I shine a light in this direction, and I measure the speed of that light, it should be the sum of the Earth's speed and the speed of light, logically, right? And conversely, if I shine a light that way, it should be the difference. You subtract this from this, and you would have the resulting velocity of light in that direction. Well, it turns out that light is directionally invariant in speed. It means the speed doesn't have any, the direction of motion of the light has no effect. Light travels the same direction, regardless of how fast the object that holds it is moving, or the source of the light, like the Earth. You shine a flashlight up into space. The beam of light going to the moon is going to travel at the same speed, regardless of the speed of the Earth. So, what's changing? If I'm sitting on this hypothetical beam of light, I observe the universe around me. You think to yourself, when I drive in my car, I go from here to New York, it's 40, 50 kilometers, let's say. If I travel 50 kilometers an hour, it takes me 1 hour to get there. Right? Distance over time is velocity. Velocity equals distance divided by time. Which one of those three terms is changing? Okay, the time. Time doesn't change the speed of light. That's the one variable in all of this that doesn't change. And that's why light is directionally invariant. Okay, and that's plays a huge role in all of this. Now, time slows down. The length of your spaceship is going to get shorter in the direction of motion, and your mass increases according to a certain formula, which is coming up next. Now, according to the gamma factor, and here, just to give you a sense, I don't know if how many, can you read these numbers? 0.0001, you guys read this? Okay, this is 0.0001, this is 0.5, 0.5 the speed of light, yeah, the speed of light. This is 95%, this is 99% the speed of light. The fastest man-made object to date is the New Horizons spacecraft that just flew by Pluto last summer. He didn't even get on the chart, and that's the fastest thing we ever made. Okay. The idea behind, at the end of tonight, when you leave here, you'll have a better idea of what this star shot is going to be. We hope to accelerate tiny little craft to 1/5 the speed of light, or 20%. You'll have a change of 2%. 1.02 is 2% change. Okay, you don't actually see any significant change until you get upwards of 99%, which is 7 times So, if I were to travel to a star, hypothetically, as a young man of, let's say, 20, and I had a brand new baby who was just born, okay? I get on my starship, and let's suppose I could travel at the speed of light. I go there to this star 70 light years away. Actually, let's make it 35. 35 and 35. For me, I see no change on my starship. But for them, 70 years have gone by. I return a man of, say, 70 years, well, no, it's a bad example, it's got to be like 7. So if I go out 7 and come back, I'm 14 years older. But he's 7 times 14. My little tiny baby boy or girl is now deceased. I returned home 14 years ago, 14 years later. That's the upshot. That's how much time slows down. If I could travel at 99% of the speed of light, figure all intents and purposes, 99 is 100, for the sake of our little argument here tonight, it's the same number. 7 light years is going to be 7.1 years to get there, 7.1 years to return. So 14 years. I've aged 14 years, normal 14 years. My little child is 7 times that. So whatever age he left, suppose he was 14 times 7.
Suppose he was 1 year at the time of March, and you ran back, he should be 71.
Yes, so I'll come back in time to see my grandchildren, or my great-grandchildren, but I'll be just another 14 years older. So that's the implications of doing this, okay? That's time. The mass and the length are also modified according to that same amount. So if I have a starship that's, let's say, 70 meters long, it's now 10 meters long when I get to this speed. It's actually compresses the length in a directional motion. But you don't feel it. You're on board the starship. You don't see everything is normal to you. But someone who watches you goes by sees it's really kind of strange thing, right? And mass too. So as you get faster and faster, at 99% the speed of light, you would need 7 times the amount of fuel to go to propel you with the same energy as you did before, because your mass is now 7 times heavier. 7 times more, not heavier. Okay, so that's the implications of this. So how do we overcome these obstacles? I open up tonight's discussion, are we forever stuck here? Can we ever make a meaningful journey, meaningful in the sense that within a human lifetime, we can accomplish some goals, achieve some mission? Okay, this is a chart that shows, here's our New Horizons spaceship right down here. Okay, that's New Horizons. 100,000 kilometers an hour. It's the fastest thing we ever made. And that was with 2 gravity assists around Jupiter and Saturn. Flew by, and the tremendous gravity of those planets accelerated even more. Okay, fastest thing we ever made. No change whatsoever. Here we are at 95% the speed of light. And you see what happens now as you get closer to the speed of light? This thing skyrockets, and it's what we call asymptotic at 1, which is infinite. Time stops, mass is infinite, and the light contracts as well. At the speed of light. So therefore, it's impossible.
If the mass is infinite, then how much force you will?
It's impossible. You couldn't move it. It's impossible. And this is why it's impossible. So how do we overcome this impediment to significant exploration of our little corner of the universe? How do we do that? Like they say in Star Trek, will we go when no one was gone before? The latest Star Trek Beyond was really good. It's kind of a little hokey in the beginning, but it actually turns out to be a nice movie. Okay. So, we're going to the stars, riding on a beam of light. We have one man's vision humanity's first interstellar mission. How are we going to do that? Yuri Milner asked the big questions in life and the universe. Are we alone? Are there habitable worlds in our galactic neighborhood? Can we make a great leap to the stars? And can we think and act together as one world in the cosmos? Now, implicit in that question is the surmounting of many obstacles, socio-political obstacles. One nation can't do this. This project, yes, we can. One nation can do this project. But to make significant progress in establishing ourselves as a sustainable outpost on the moon, or perhaps maybe even Mars, would require the entire world to be behind and one effort to do this. And we have huge obstacles, not technical obstacles. We have the technology. We have to overcome other things. Okay, and that's implicit in that last question he's asking. Okay, he was born in 1961, and Yuri Gagarin completed his suborbital flight on the Earth. The first man to orbit the Earth was Yuri Gagarin, and Yuri Milner, a Russian. He's also a Russian. Was named in honor of his fellow countryman back in 1961, who completed the first orbit on the Earth. Okay. So, what is the proposal? The Starshot proposal is a 1 gram mass scale nanocraft, which is what? The mass and dimensions of an iPod or an iPhone, or take half your mobile phone, about that big, right? Accelerated to 1/5 or 20% the speed of light to reach our nearest stellar neighbor, 4.2 light years distant in less than 23 years. It's 4.3 light years or 4.2 light years. So it's a factor of 5 greater than 4.2, which is about 22 years. It would take 22, 23 years to get there. And it's a one-way trip, not coming back. And it's going to fly through that system like, in a blink of an eye. At 1/5 the speed of light. It's still really fast. Even though it's a tiny little thing, it's traveling, and you can't stop it. How could you stop it? How are we going to do this? Why did we choose something so small? Well, you'll come to learn that the amount of energy required to accelerate anything to that speed is enormous. The nanocraft will be accelerated to 1/5 the speed of light using a light sail. Okay. When you go out on a bright sunny day, you don't feel any pressure from the sun. Right? You might feel pressure from a nice breeze or wind and so forth, but you don't feel anything. But in fact, the brilliant sun does provide a certain radiation pressure from the brilliant light. And if you have a large enough sail, very thin, only a few molecular layers thin, you can actually use it in this way. Basically as a sail to catch the sun's light and pull something if it's small. That's why these objects have to be so small. One gram is maybe the mass of a pen. Maybe a little bit more than a pen, but it's not that much.
It's going to be 20 grams.
Yes.
It's going to be 10 or 20 grams weight. Yes.
Yes.
An estimate mass will be 10 grams, more than 10.
Yes, yes. How are we going to do this? 100 gigawatt. Now, 1 watt, everybody knows what a 100 watt light bulb is, right? Okay. Imagine a billion of those. 100 watt light bulb, a billion of them. That's 100 gigawatts. That's how much energy is required, sustained over 10 minutes, to accelerate something 1 gram mass to 20% the speed of light. And you'll see how this is going to work. It's an amazing idea. Okay, 100 gigawatt ground-based phased array laser, which means they all act in concert, will accelerate thousands of these nanocraft-equipped light sails to 20% light speed in a distance of 2 million kilometers in the space of 10 minutes. That's about 5 times the distance to the moon. That acceleration is a staggering 91,000 Gs. 91,000. So when you take off in a plane, gentle acceleration, you feel yourself being pushed into the seat a little bit, that's about 2 Gs. Maybe not even 2 Gs. A high-speed turn in a high-performance aircraft is like 5 or 6 Gs. 91,000 Gs. Okay. The energy required, so when we work out the numbers in a space of 10 minutes with that initial baseline power, the energy required to accelerate it to 0.2 c. C is the universal symbol for the speed of light, capital C. In 10 minutes is equivalent to 1.8 terajoules of energy, the equivalent of 500 megawatt hours, sustained 500 megawatts for 1 hour. You get your light bill, you bill every month your electric bill, how many kilowatt hours do you use? 100, 50, 200, something. That's kilowatt hours. This is megawatts. This is the output of a small nuclear power station. For 1 hour, the sustained output to accelerate one of those tiny little things that are enormous speed. Okay? Or it's 4% of all the energy released by the Hiroshima blast to accelerate a tiny little thing to 20% the speed of light. This is what it's all about. That's the light sail. This is the ground-based phased array lasers. Watch. That's going to accelerate. So that's the, what I mentioned a few moments ago about the sunlight having the radiation pressure. That's what the pressure of all those lasers, the combined energy of all those lasers. Keep it focused on that light sail for 10 minutes. It's going to accelerate that thing to 20% the speed of light. Now that's arriving. That's Alpha Centauri, which is basically a carbon copy of our sun, by the way. And there's a smaller, cooler companion, Proxima Centauri, which is a small red dwarf star, which is smaller. And they just recently found, they believe there's a high confidence in the discovery of it, an Earth-mass, Earth-class planet in orbit on Proxima, which gives us a lot of encouragement. And that's why this star shot, that's why one of the reasons why they chose this as a target is the discovery of an Earth-like planet in orbit. Okay, this was in the New York Times. This was in the press. It was basically published in quite a different outlets. Okay, they 20 years, that was just a round number, it's a little bit longer. But this is the brainchild of Yuri Milner. Now the big deal with Yuri Milner, he donated $100 million in seed funding to start the project. And it's up to others to, that's a lot, it's a sizable amount of money, but I think they're going to need more. It's an open project. Everybody's welcome to contribute. It's an access. It's open and accessible by the public. If you have any ideas, the website is on the slideshow. At the end, you can see the URL. If you want to contribute, if you're interested, you want to find out more information about this, it's all open to the public, which is really nice.
Sir, how long it will take this spacecraft to reach there?
22, 23 years. Yes.
What's gonna be on the map?
That's a good question.
Experiments?
Yeah,
So small.
so who's working on this? Yuri provided $100 million in seed funding, assembled a blue ribbon panel as initial collaborators that include everybody who's Freeman Dyson, famous physicist, widow and partner in science to the now late great Carl Sagan, and Dre. Okay, it's an open project inviting public input and participation. What are some of the challenges? I think the question was asked about what's it going to have on there, right? Let's take a look at the challenges first, and that'll kind of give us a sense of what we can actually do. Right? How are we going to transport, or how are we going to hold the charge for 22 years? Battery. If you don't start the car, it's 2, 3, or 4, maybe a couple of months, the battery goes dead. We're developing incredible battery technology now. Elon Musk is doing a lot of building a big factory. And they're building really great batteries, but they got to make them really small, really tiny, something that could fit inside your wallet and be light enough to put inside this thing and last for 23 years. That's a tall order, and that's the biggest problem right there. We have the technology now to build that light sail and accelerate it, but how dependable will it be, right? How are we going to transmit the data and the images back? In cosmic terms, 4 light years is nothing. Okay, but for us, this tiny little thing has got to. We've got to have a tremendous receiver on the other end. How we can do it? These are all real technical problems, but this is a real project. Okay. Mission continuance over the mission lifetime, 22 or 23 years. When NASA designs missions, they always look for the youngest. Actually, age goes into it, as opposed to some idea that people are being discriminatory because you're not hiring an older person. They want the person around in 10 years or 15 15 years. They don't want them retiring unless, God forbid, something happened. So they always think of these things, these long-term, like the Cassini mission to Saturn was launched in '97. It arrived in 2004, and it's still there. It actually, the mission sunsets next year. Basically, there 20 years. So whoever started that mission is still there 20 years later. So these are the time scales that are involved. Will we have the same people around? Will things change? Will the ideas change? Will this mission kind of be forgotten? We got to maintain the funding or the support over over the lifetime of the mission. Pointing accuracy of the laser, at least on the acceleration phase. You got to keep that laser dead focused on those things. But if you point off, if you feel off like half a degree, you can send it off into another part of the galaxy. Okay? What unknowns are between here and Alpha Centauri system that require hundreds or thousands of nanocraft to maximize the probability of success? In other words, we're not just going to send one. We're going to make hundreds, maybe thousands of them, and launch them all at the same time. And probability, there's a higher probability of success in numbers. The more you have, suppose something happens, maybe you lose 10% of them. At least some of them will survive. Most of them will survive to send back that information. It's a flyby mission only, so there's no do-overs. Right? And obviously there's minimal directional control and guidance once the acceleration is achieved. Right? Once you reach cruise speed, you can't do anything. They're on their way. Newton's first law: anything in motion will stay that way until something changes it. Newton's first law. Right? And they're subject to that. Okay. Why the Alpha Centauri star system? That doesn't really go to answer your question. What could we put on a tiny little thing? Like right now, you have your mobile phone. You got a camera on there. You got a computer. You got a phone. A phone. Phone home. ET phone home. Right. It's the same thing. Right. So you want to make a long distance phone call, 4 light years away. So these are the technical problems, and that'll give you some kind of sense of what we can put on this little tiny thing, right? Okay, why did we choose Alpha Centauri? It's the closest star system to ours. Alpha Centauri. It's actually a triple star system. There's Alpha Centauri A and B, and Proxima Centauri, which is considered Alpha Centauri C. Alpha Centauri is in itself a binary star. A star like our sun, a carbon, literally the same type, class, temperature, everything as our sun, and a slightly smaller, less massive, cooler star. And then at a distance, you have Proxima orbiting those two. They're in their own orbit, so it's considered a triple star system. Right now, in this epoch in history, Proxima in its orbit is closest to us. Okay, so this ship, once it gets there, the orbit's not going to change much. It's a very large orbit, so by the time it gets there, Proxima will still be the closest star. So when these things arrive in 25 years, we're probably going to fly by Proxima. Although 1 degree here, 1 degree 4.5 light years away from here, could be the whole system. Could be a huge swath of space. So, because of the distance and the speeds involved, we can realize the mission goals within a human lifetime. So this is going to probably take another 10. The way things look like by 2025, 2030, we're going to have a smaller, less ambitious goal of sending some of these to Mars. The travel time to Mars, normal light speed is like 20 minutes. So this would take 20 times 5 is 100 minutes, an hour and 40 minutes. We'll be there at Mars, and we'll see if it works. Okay? It's like I mentioned, stellar analog of our sun. High probability. Right now, we've found, this only was discovered this last year. We have an Earth-mass planet orbiting Proxima. So that means what? That means it could sustain, could be already have life. We don't know. We see that it's orbiting. We can tell by the star's perturbation, the movement of the star. We can tell that there's some smaller thing orbiting it. Kind of tends to pull it off its center. Even though its star is much bigger than the planet, still gravity, you can measure gravity down very precisely. Proxima is also a cool red dwarf star, part of the triple star system. Okay. So where is it? Where is Alpha Centauri? If you were to go out tonight, where would you have to look? Well, you can't see it from New York. You have to actually travel down to Key West. You barely see it. Ideally, you have to go down to Mexico, maybe below the equator, to see it properly. Okay. So this will give you a sense of where it is. Okay. Rigel Centaurus is another name for Alpha. This is it right here. Right, I'm zooming in on it. These images were produced with a program called Stellarium. It's free downloadable. It's a great program. Rigel Centaurus. And that's the actual picture obtained with European Southern Observatory's telescope in Chile. This is combined light of both Alpha Centauri A and B. This proxima, tiny little red proxima down here. So if basically take about half of this light, that would be the sun. You get a sense of the luminosity difference between this and this. This would take about half of this as the sun, right? Compare that to this. You can see how much more powerful our sun is than a tiny little red dwarf. And our sun is actually by the same scale as tiny compared to some more tremendous stars, very powerful stars. Okay, that's an image of Proxima. Taking the whole telescope. Please keep in mind, though, that these spikes are artifacts of the optical system inside the telescope. These are supported. The telescope, you've got a big concave mirror at the bottom, you've got a mirror up top here, and the support system at the top of the telescope creates what we call diffraction. And that's what this is right here. Okay? That's Proxima Centauri, the telescope. And this is what this distant world might look like if we were to travel there, right? That's Proxima. This is some alien planet. We have no idea what it will look like. Some artists, this is what they thought. Okay. If you're interested in more information, the breakthrough initiatives have three current portals right now. Breakthrough Listen, Breakthrough Message, Breakthrough Starshot. Yuri Milner has financed all three. Okay, each one we give $100 million to. Right now, we just talked about the Starshot. Breakthrough Listen is a project where we're listening to evidence of intelligent signal. A real substantive project with real funding, it's like a full-time occupation. We're listening to the sky in many different wavebands, looking for the possibility of interstellar communications. Okay. Breakthrough Message is to see if ET is using lasers to actually communicate using. Right now we have, who has fiber optics? So you have FiOS, you have fiber optics, right? So what the thinking is, well, maybe ET is using lasers. It's the same principle that it's in the fiber optic scale. Right? And then we have Breakthrough Starshot. Each one has